Hi viewers, welcome to all. Here we are discussing about a project Reconfigurable Architecture for Real-Time Decoding of Canonical Huffman Codes. In a recent technology of digital network will transfers and receives the data with more complexity due to number of data bits and number of memory operations. Thus, it will take more data losses and low throughput. Therefore, this proposed work of this paper presents a lossless data compressions and decompressions with a less memory architectures using canonical Huffman compressions and decompression technique. Okay, so in this case, here the Huffman machine will present a lossless and less memory configurations, and it supports a multi-bit operations of data compressions and decompressions. Here, this technique will present the input as 640 data bits and the compressed output as 90 data bits using variable length with a canonical Huffman encoding method, and the same will be decompressed 90 data bits as an input and decompressed 640 data bits using canonical Huffman decoding method. Finally, this work will presenting in Verilog HDLs and synthesized in Vertex 5 FPGA and get all the results in terms of area, delay and power. So this reconfigurable architecture of real-time canonical Huffman encoder we have present with 3 papers. Okay, so this is a paper 4 encoder, a high throughput VLSI architecture design of canonical Huffman encoder design. Okay, so this paper they have splitted with this architecture in figure 2 system circuit block diagram. Okay, so as per this architectures we have designed the process of canonical Huffman encoding. Okay, and the decoder architectures will be used in this paper reconfigurable architecture for real-time decoding canonical Huffman codes. So this paper given some architectures, okay, Huffman tree codes, okay, and canonical Huffman codes, how it will be decoded, how it will be encoded. Okay, and we have used some other base paper also. This is a one more reference paper, and this is a one more reference paper for fast canonical Huffman decoder. Okay, creating of decoding segment and dexes. Okay, so based upon this reference papers we have created a document for this project. Okay, so this is a Huffman encoding and decoding method based structures. Okay, so here we have used as a 160 data bit as an input. Okay, so 160 bits means here we are using 20 characters. Each character will consider as a 8-bit input. Okay, so this 8-bit input will present in ASCII codes A, B, B, C as a character. Okay, so this input we are given into the Huffman encoder machine. Okay, and we will get a compressed data as a 90-bit. Okay, and this method will be followed with frequency count, sorting, bit mapping and code table. Okay, so initially the frequency count will calculate the number of characters. Example, A equal to 4 times and B equal to 7 times, C equal to 3 times and D equal to 2 times, E equal to 4 times from the input. Okay, that is a frequency count. Okay, after that it will come with the sorting part. Okay, so sorting means we need to arrange the number of frequency count in the ascending order. Okay, so 2, 3, 4, 4, 7. Okay, so as per this sorting we need to create a bit mapping state machines. Okay, so this bit mapping state machines will be function with this characters. Okay, so here characters means, so we are used A, B, C, D, 4 characters only. So not we are design A to Z characters. Okay, so if you need A to Z characters, we need to create a more number of state machine architectures. Okay, so this is a 4 character based state machine architectures. So here as per this sorting, first we need to take the least value. Okay, so it starts from the D. Okay, so this least value will described with up to the highest value of the state machines. Okay, after that we need to design a code table. So this code table will configure with this state machines. Okay, example, A means 0 1 0 1 and B means 1 1 1 1 and C means 1 0 1 and D means 1 0 0. Okay, so and E means 0 0. Okay, E means 0 0. Okay, so based upon this bit mapping we have designed a code table. After this code table we need to construct a encoding data packets as a canonical form. Okay, so this canonical form you can refer with in Wikipedia. Okay, so here they are given some formats. Okay, so 2 followed by 11 and 1 followed by 0, 3 followed by 101. Okay, so as per this we can possible to design a canonical Huffman encoding. Okay, so here 2 followed by 01, that means 2 bit followed by the character of code table value 01. Okay, that means here A, okay, A followed by 01. Okay, B means it's a 2 bit, 2 followed by 1 and after that B again 2 followed by 1. Okay, so based upon this encoding we will get a 90-bit data output. Okay, so this 90-bit data output we are given into the decoder. Okay, so here this is a decoder architecture. Okay, so before decoder architectures, for reference we are created this table. Okay, so we need to analyze the encoding output. Okay, so this 201 means 201, this is a 201 211. Okay, so this is a buffer data. Okay, 211. Okay, so we need to describe this one, then after we will design this architectures, the block diagram of Huffman decoding. Okay, so here we are given a 90-bit code word from the encoder. Okay, and done signal. Okay, so once the encoder done, it will create as a done signal. Okay, so this code word will given into the parallel shifter, FSM bitmap decoding and symbol table, and finally decode buffer. Okay, so as per the reference with this architectures. Okay, so input stream to output stream. Okay, shifting. Okay, so FIFO buffers, everything they are used with the state machine. Okay, so you can also refer with this paper. So this paper presents with the section 4 canonical Huffman decoder architecture. Okay, so the table 1 will describe the symbol length, code 1, code 2, code 3, and this is the architecture for canonical Huffman decoder architecture, figure 6. Okay, so initially they are loaded with the table generations. Okay, and symbol table, base table, and symbol decoding. Okay, using this reference we are designing a Huffman decoding architecture. So this is a novelty based one. Okay, and as per this architectures, the bit mapping we are designed with a state machine. This is a FSM bitmap decoding state machine. Okay, and finally we are written with the Verilog HDL coding. So this is a coding part for the canonical Huffman decoder. Okay, so this is a state machine. Okay, so initially we have designed with the canonical Huffman machine and canonical Huffman decoder and file reading and file writing. Okay, so why file reading and file writing means we are used to two file. Okay, so this is an input file. Okay, so here we are given as a character A, B, B, C, D as an input character. Okay, so this character we are given as an input file. So this file will be read using file reading code and it will be stored in the register input write data register. Okay, from the file reading with the start signal. Okay, so once the data file will be read, the data will be given into the Huffman machine. Okay, so here is the data input. It's a 160 data bit. It will given directly to the Huffman buffer. Okay, so data input, Huffman buffer data in, and frequency count, sorting, bit mapping, and code table. Okay, so I'll show some more reference paper for this encoder architecture. You can refer this, a high throughput hardware oscillator for lossless compression for DDR4 command trace. Okay, so this is a method for Huffman decoder, Huffman front part and Huffman back part. Okay. So using this reference we have designed this architecture. Okay, so frequency count, buffer, bitmap table, bitmap controller. Okay, and the state machine, everything we have done with the encoder. Okay, so this is an encoder architecture. So Huffman buffer, frequency count, sorting, and bit mapping, and finally code table. So once The code table produce the code words. Okay, this is a 90-bit compressed data. Okay, it will given into the Huffman decoder. So here the decoder will present with barrel shifter, FSM bit mapping, decoding, and symbol table and decode buffer. Okay, so this decode buffer will produce the compressed decompressed data, that is a 160 data bit. Okay, so it will given finally into the test bench. Okay, with the file writing, and finally we are taken as a compressed data bit. Okay, here you can check the output. Okay, so this simulation result we can done with modelism. Okay, so here we can run it. Okay, here you can check the Huffman machine encoder and Huffman decoder. Okay, so here this is the input. Okay, so this input will be in the reverse form as a input of the file. Okay, so here the file reading means it will start with A, B, D, A, B, C. Okay, so it's a LSB will be first. Okay, so this data it will be given into the encoder, and this is a symbol count and frequency output and symbol pulse. Okay, and this is a for sort frequency data, sort symbol data. Okay, so bitmap table, bitmap symbol output. Okay, so everything done, and finally it will come with this code word. Okay, so the code word means it's a 90-bit, 89 down to 0. Okay, and data input is 160 data bit, so 159 down to 0. Okay, so this 159 down to 0 it will be given into the Huffman decoder machine. Okay, so here. Okay, so here the code words will be loaded here. Okay, so Huffman decoder, and the Huffman decoder will start the process as per this input. Okay, so it will start with the barrel shifter. Okay, and it will find out the maximum and minimum point with the FSM decoding. Okay, so this is a state machine process. Okay, and this is a symbol table. Okay, so it will fill the symbol. Okay, as per the values. Okay, so A, B, D, A, B, C, A, E, okay, B. Okay, and this is a decode buffer. Okay, so finally it will buffer the data and it produce the output in the final case. Okay, the total time of encoding and decoding for 20 characters, it will take 2.673 microseconds. Okay, so this is a decode value. Here you can check that the decode value, and here you can check it, it's a encode value. Okay, so here you can check the value. This one and this one. Okay, and for the synthesis, we have used as vertex 5 FPGA. So this is a 4 encoder. Okay, so here you can check the number of slice registers, LUTs, occupied slices, and IO base. Okay, synthesis report you can check delay. Okay, 8.016 nanoseconds. Okay, and this is the Aritix schematic for encoder. Huffman buffer, frequency count, sorting, bit mapping, and code table. And this is a 4 decoder. Okay, so here you can check number of slice registers, LUTs, and occupied slice IO base. Okay, and synthesis report you can check delay for total 4.019 nanoseconds. And this is the Aritix schematic for decoder. So barrel shifter, FSM bitmap decoding, symbol table, and decode buffer. And finally we have come with the comparisons document. This is for comparison for encoder machine. Okay, and this is comparisons for decoder machine. Okay, and we have written abstract document for this project. So this is the abstract document. So base paper abstract, improvement of the project, proposed title, proposed abstract, okay, existing notes, okay, disadvantages, proposed systems, advantages, okay, literature survey and related notes of the project, finally references. Okay, thank you.
If you need more video related to VLSI project, please like and subscribe this channel.
Hi, welcome to NXV Innovation Semiconductor IP Design, Development, Services. Here, NXV developing solution to provide core products and application to customers with a wide range of solution that include custom ASIC, FPGA, DSP, embedded system, wireless technologies.
Having lustrum of expertise and satisfied customers, NXV have the capability to deliver solution that is fully meshed with customers' business requirement, meeting the highest standards.
We have a well-qualified R&D unit for wireless, embedded, FPGA, ASIC design services. Our sound technology and knowledge base have helped us to create products using emerging technologies that include FPGA, VHDL, Verilog HDL, System Verilog HDL, UVM, OVM, VVM, DSP, Bluetooth, Wi-Fi, RF, CDMA, and other related technologies in the areas of industrial automation, telecommunications, consumer electronics and automotive applications.
NXV development products on high-speed data transmission, secure video processing, secure digital demodulation, signal processing and applications, intelligent robotics.
NXV, also developing VLSI project for all domain, low power, high speed, area efficient for B.Tech, ME, M.Tech, and PhD students.
We are successfully completed more number of VLSI PhD with publications. Get in touch with Best Semiconductor IP Development. Contact 978-944-3203, nxv.innovation@gmail.com.